about like racing, which might not touch logic so much. So again, stop me at any time. So we'll go through some formal methods for system verification, linear temporal logic, and then after that, we'll go deeper into minimum violation planning. A lot of preliminary material you can find on this Principles of Model Checking book. It is pretty good. If you want to get involved in formal methods, this is one of the first books you should read. So let me give a little bit of motivation of why we are doing all this, right? So I guess one of the events that really stimulate the research in autonomous driving is the DARPA Urban Challenge. Caltech got involved since the Urban Challenge 04. And back then we have this car named Alice in 04. Let me show you some video. It was mostly driving in the desert. So, the major problem there is to find a road, figure out where to drive, where static obstacles are. So this is mainly just driving from A to B, avoiding obstacle and stay on the road, right? In 2007, they changed the race to urban setting. And all of a sudden, the challenge kind of changed from finding the road to how do we incorporate the rule of the road, right? So in 07, we have to handle situations like this where you get into intersection. You need to figure out who has the right of way, who get there first, and keep track of the queue. And when it's your turn to go, then you have to go. And because of that, we started implementing a lot of software stack to handle situations like this, right? So on the left-hand side here, we have what we call perception system. Its responsibility is to figure out the best estimate of what the world looks like, right? And then on the right-hand side, we have the planning and control system. Right, you'll see that we have to invent a lot of things within 1 year. Right? So back then in 07, we don't know much about formal methods. What we implement on the planning control side to handle traffic rules, and interestingly, most of the teams have pretty much the same architecture. We start from mission planning. So this keep track of what data give us is the sequence of points that we have to visit, right? And we have to visit them in order. So mission planner will determine where is the next goal point that we should go to. Traffic planner then handle more of the local interaction and all the logic, whether we have to stay in lane, whether we are allowed to do avoidance, reversing, whether we should stop at intersection or we should proceed. Path planner is planning a path based on the logic that traffic planner generate. And after that, it's a typical control problem, right, where we follow a path. Now, back then, we don't know about formal methods. So traffic planner is mostly a finite state machine. I think most of the team did this, and we all suffer the pain. I actually wrote this component myself. You can see how complicated it is. Typically, I think when people start writing finite state machine, it would seem simple. It would seem purely reasonable, logical. When we started writing this logic planner, we only have 3 states, right? Drive, stay in lane, or drive and then overtake or stop within lane. Right? But as we see the situations more and more, as we keep testing, we have to add more and more states to handle some corner cases. And this is where it sort of ends up. This is only when we stay on the road. We have another finite state machine for parking, for reversing and intersection handling. So you can see how complicated this can be. And at that point, it was almost impossible to verify this logic. This is some statistics when we competed in the race, you can see that so there was one of the run where we have what we call the bare mode. This is where we reduce the buffer to 0. It's sort of, if we have to scratch some object, that's okay, because we still want to get to the goal and win the race. So this is sort of the motivation behind this. Again, at that point, we didn't know about formal methods yet, and there's no way we could verify or build this and or guarantee correctness of this at all. So how does formal methods play a role in here, right? So in formal methods, we usually have 3 main inputs. We need to understand how we model our system. We need to understand the assumptions about the environment we are operating in. And finally, we need to know the requirements or what are the desired behavior of the system. Right? So essentially, from these 3, there are 2 sides of the components. One is the system and environment model. And on the other hand, we have the formal specifications. So let's say we design the controller by hand. Right? What we can do with the system, the controller, and also specification is to ask a verification problem, whether the system with the controller actually satisfy the specification. Right? And if it satisfies, we should get a certificate that it satisfies. It's not just, we run a few times and see that, it works, because in this case, there are infinite possibilities of what could happen. Right? So testing simulation cannot give any guarantee. Formal methods, on the other hand, could give this kind of guarantee. And on the other hand, if verification say the spec is violated, then it will provide also a counterexample. So that's the verification side. Another question we can ask is, given a system and the environment model and also the formal specification, another question we could ask is, can we actually synthesize the controller automatically in a way that it is correct by construction, right? So in this synthesis process, if it actually synthesizes a controller, it will guarantee that the spec is satisfied, or it will say that no such controller exists. And in that case, you might have to go back to the specification. Does this all make sense? Sorry, I cannot see any of you right now. Does this make sense?
Yep. So earlier there was a question from somebody. They wanted to know, what is a LiDAR? LADAR. I think it's the same as LiDAR. It's
a LiDAR. Yeah, it's a LiDAR. Sorry, I could not hear you when I present. Is there?
Nobody spoke it. They just wrote it in the text box, and I think that when you have something, you won't be able to see it. So if there's any questions that are text only, I'll jump in and repeat them for you, if you'd like.
All right, sounds good. So let me go back to the slide. Oops. All right, so this is about formal methods, right? Now, let me first talk about the right-hand side of this picture, about formal specifications, right? So as we may know, a lot of time traffic rules, for example, could be quite ambiguous. There are quite a number of times when I was working on autonomous driving where, there were a few of us in the room and we read the same rule. We thought each of us understood it, but when we check against each other, the way we understood it are totally different. So simple word like, slow down. What does slow down mean? Is that sometimes what they really want is some bound on the speed. And sometimes they really mean some bound on acceleration. So it's not very clear what really slow down means. And there are many examples in traffic rule that could be quite ambiguous. But one of the key components of formal methods is to specify precisely what you want the system to behave. Right? And a lot of time we use the language from computer science called temporal logic. And in particular, one of the language that is used a lot within temporal logic is called linear temporal logic. Right? So in this language, it so linear temporal logic sort of extend the standard propositional logic by adding the notion of time. And by what I mean by time is just the sequence of states. It's not like the actual time. So in this case, it adds temporal operators, right? So that include next and until, right? These are the basic operators. And now, in propositional logic is evaluated over a single state. LTL, on the other hand, is interpreted over an infinite sequence of states, or what we call a path, right? So if we have atomic proposition A, what it means when we have a run, and a run satisfy A means just the first state in this run satisfy A. So that's the first example. After that, it doesn't matter. Next A means that the next state in the sequence satisfy A. So the second state in the sequence have to satisfy A. The rest doesn't matter, right? Until A until B means A has to hold, and there must be the point of time where B hold, right? And after that, it doesn't matter anymore whether A holds. And that's the third example, right? And we have this notation. Sigma model is like satisfied the specification. So that means a run satisfied the specification. Does that make sense? Any questions so far? This will be the language that we will continue to use throughout this lecture. All right. There are other derived important operators, including eventually. So eventually, phi is equivalent to true until phi. So that means phi has to become true at some point in the future. Right? So that's the first example. The next operator is always. So always phi is equivalent to not eventually not phi. So that means at every single point in the execution, phi has to hold. Right? So if we say always A, that means A have to hold at every single state in the execution. Right? And there are other important formula. For example, response formula would say that P imply eventually Q. Right? So once P is true, that means at some point in the future, Q has to hold. Right? Always eventually P means that P has to hold infinitely often. And eventually P means at some point in the future, P has to hold, and after that, P has to hold for the rest of the run. Right. So those are sort of, important formula that has been used a lot in robotics in particular.
Maybe somebody from the class could try and come up with an example of always formula for driving and an eventually always formula for driving, just to make sure that we're not getting lost. Anybody?
Yep. Anyone?
Okay, somebody says time to collision should always be greater than some threshold. I think that's a good example. What about eventually? Yep. Eventually always, or just even eventually? What if you go to a four-way stop? What would be a thing that you'd want to say there?
Well, you'd eventually want to stop, and then eventually want to go.
Yeah, I
mean that makes sense. I mean,
yeah.
I guess it depends on where you're at. Are you saying you're already stopped at the intersection?
Yeah, let's say you're already stopped.
Oh, then you eventually go.
Yeah, and I think maybe for this actual stopping, that maybe eventually is not the right version. Like it has like
Yeah.
your position in space as well, which I'm sure will be explained that you can use these formulas to describe aspects of that as well.
Right. So intersection, for example, what we could say is to use until, right? So you can say that you should be stopped until the intersection is clear, and at which point you should go, right? So you can see that LTL is very similar to natural language. It's just the way you speak, but it makes it much more precise because it has a well-defined semantics. Any other questions before I continue? All right. Okay, so this is sort of a more formal definitions of the semantics of LTL, right? So LTL, as I said, is interpreted over a word, right? And given a formula phi, we say that a word is the set of all the sequence of labels that satisfy phi. And we have the satisfaction relation, which means that, okay, so it's the smallest relation, and we have this table below that explain what it means, right? So phi always satisfy true, right? So if you have a formula that say true, whatever sequence you keep will always satisfy true, right? Phi satisfy A if A0. So A0 is the first state in phi, in sigma, right? So a label A has to be in A0, right? And the conjunction is similar to what we would say in propositional logic. Negation also. Next means that the next state has to satisfy, and until means at some point, at some position j in the future, phi 2 is satisfied, and for all I before that, phi 1 has to satisfy. So this is a more formal definition of what I described informally earlier.
So there was a good question from the class. Somebody wants to know, is there a way to say that something should happen like 100 steps from now? And as you described next, the student also said, well, other than using next 100 times.
Yeah, so there are a few things you can do. So with if you just limit to LTL, you can say, yeah, of course, the brute force one is that you put the next 100 times, right? Another way is you introduce another variable that is a counter, and this one is incremented every time in the execution. Apparently, this one will be infinite, right? It goes to infinite, and then the formula will be with respect to this new variable, and also the original property you want to satisfy in the next 100 times. Yeah, there are also other languages that recently came out. LTL is really old. I mean, this is date back to like 1980s or so. There are other newer language that might be more suitable for control, like STL, signal temporal logic. So they use mostly the same symbol as in LTL, but they have the time semantic there also. So for example, instead of saying eventually something happened, in STL, the eventually will have the bound on the time steps. Right? Does that answer your question?
Yeah, the student said thank you, I think, in the comments.
Thank you.
So yeah, that's good.
Thank you. All right, so that's LTL. So let me give one example of what we could say, right? So this is, as we are focusing on autonomous driving, let me give an example about traffic light, right? So traffic light can be green, yellow, or red. Sorry for the misspelling. So in this case, atomic proposition could be just the color of the light, right? So example of specifications we could say is, for example, what we call liveness property. Traffic light is green infinitely often. So that would be always eventually green, right? Or, a little more complicated spec, right? once the light is red, it cannot become green immediately. One example is, always red imply that not next green, right? So this is just writing exactly what the word was saying. A more detailed example, right? A more complicated one. Once red, the light always becomes green eventually after being yellow for some time. Right? So there are many ways of writing this down, and this show how ambiguous English would be. Right? So one example is that always, in parentheses, red, right? So that means once red, then eventually green, right? But it cannot be green until it becomes yellow first, right? So that's one way of interpreting this informal English description. We can also write it in a different way, right? Always, in parentheses, red, right? Now, it says that next, red until, right? And then there's this big group, yellow and yellow until green, right? The two formula are not equivalent. Depending on how you interpret the English description, one person might think it's the first formula, another might think it's the second formula. Right? So this is some example of how things that seems quite clear in English could be interpreted differently, right? And LTL can help us to make this more precise. Right.
So there was a question.
Yes.
The second formula.
Yes.
Once red, the light cannot become green immediately. Somebody wonders, the way that it's written, is it ever possible for it to become green? He thinks that
so if it doesn't become green at all, it also satisfies the formula, right? So if it's red forever, right? If the light is red forever, it will satisfy the formula.
Mm-hmm. Yeah, I think maybe what's happening is people are thinking it goes from green to yellow to red in the US. I don't know if I know some other countries give you a warning that it's about to turn green.
Yeah, I think in Europe it has this red yellow that comes at the same time. So this finite state machine is sort of in Europe. Some countries in Europe, I think it has yet red and yellow coming together before the light becomes green.
Yeah, and, I mean, on another level, it's very interesting that we have people from many different countries here, and we're all interpreting what should happen with the light differently, which is probably a big issue for autonomous driving. So maybe I'll touch on that later. How the rules might vary by situation or country. Yeah. Okay. Student's question is.
Any other questions? Thank you for helping me to explain this. Any other questions? All right, let's continue. So that's an example on LTL. Now, to date, I mean, as far as I know, given an LTL specification and the system model, right, there are sort of 4 categories of synthesis techniques. One is based on pure traditional model checking. The second category is probabilistic synthesis. So this would cover like MDP, POMDP. The third category is reactive synthesis. And the one we will focus on today is called minimum violation planning. So each of these has different assumptions about the model of the system. Right. So in the first and the last case, we assume deterministic system. In probabilistic synthesis, as the name suggests, it assumes probabilistic system. In reactive synthesis, we assume sort of adversarial non-deterministic systems. In terms of the guarantee, right, model checking guarantee that the controller, if it can synthesize, the controller will satisfy the spec. In probabilistic synthesis, instead, it tries to maximize the probability of satisfying the spec. In reactive synthesis, the guarantee is that the controller will satisfy the spec for all the possible adversarial actions. In this case, it relies on some assumption about what are all the possible adversarial actions. In minimum violation planning, it minimizes the violation of the spec. So the nice thing about it is that there's no infeasibility, right? It will always give an answer, and it guarantee that the answer it gives is optimal with respect to the spec. Right? Computational nature, I mean, this is based on my own judgment. So for cross-system synthesis or traditional model checking, this is usually quite fast. It can handle quite large system. You should take a look at the size of the system that JPL could handle nowadays. So that's large. It can be used offline, online. Probabilistic and reactive, I would say that because of the computation complexity, mostly they are used to synthesize offline strategy and then apply the strategy online. Minimum violation planning, because it rely on deterministic system. So mostly it is to be applied online. So again, it is fast because it's essentially another model checking with some cost. And rely on real-time replanning to respond to quickly changing environment. For closed system synthesis, it rely on the satisfiability of the spec, right? So if there is no controller that will guarantee the satisfactory of the spec, then it's just say, you know, it just give up. It doesn't give you anything. Probabilistic synthesis and reactive synthesis both rely on having accurate model of the environment. Minimum violation, on the other hand, it relies on having a real-time replanning to respond to quickly change in the environment. And these different techniques has been applied in various applications.
So somebody wants to know, what is the difference between a probabilistic system and a non-deterministic system?
I see. So for non-deterministic system, there is no probabilistic notion. So in probabilistic system, you can say that, let's say another car would change lane with probability, say 0.7, right? So that would be a probabilistic description, right? So another car has 0.7 probability of changing lane and 0.3 of staying in lane. In reactive synthesis, when we say it's non-deterministic, we don't even know this probability. So we only know that the other car might be on the lane or change lane, right? So probabilistic would require quite a bit more knowledge of how the environment is behaving. Does that answer the question?
I think it does. How would you consider something where all the transition probabilities are uniformly likely? Is that it's pretty similar to non-determinism, or no?
Well, no. So that means you know that all the transitions are likely to happen. So in reactive synthesis, right, the guarantee is that no matter what transition is being taken, the controller has to satisfy the spec. In probabilistic, that's not the case. So it just tries to optimize the probability that the system satisfies the spec, right? And the probability is based on this transition probability.
And so I have personally a question, which is different from these. How does the sort of dynamics of the system play into the scalability or availability of any of these methods? I mean, we're talking about robots, not just the finite state machine, right? It's the state machine glued onto the system dynamics.
Right. That's also a very good point. So a lot of these techniques, they apply, I mean, they were invented on the computer science side, so everything is finite and discrete. There are techniques from control domain to abstract a dynamical system, so infinite state continuous system, into a finite state system. Mostly these are not like exactly equivalent, but we rely on over and under approximation to abstract the continuous domains. Let's see. So I would say there are sort of two main techniques of abstracting the continuous dynamics, right? One is what we call like abstraction. So that means we sort of grid the state space into a finite number of cells, right? And then we ensure that there exists, so if there is a transition in the finite state system, there must exist a controller in the continuous domain to bring the system from one cell to the other cell, right? So that's sort of the main idea behind abstraction. Another technique, which I will I'm not sure if I will have time, but if we have time, we'll cover is Emilio Fasoli, he called it concretization. So instead of gridding the state space into cells or region, we sample the state space. So we have a finite sample of states from the continuous domain, and with that we have a finite number of states, right? And we draw an edge between states if there exists a controller between the two states. So I would say there are sort of roughly these two ideas of how you transform the infinite state continuous system into a finite state model.
Okay. Yeah. We recently in class had a discussion about the Intel Mobileye responsibility sensitive safety. And,
yep.
And so they do sort of an abstraction where they say, well, I have a controller that will help me switch lanes. So I just wanted to point out to the class that I think there's a similarity in the approach there, but the Intel one is less formal in some sense.
Yep. Yeah. Okay. Any other questions before we move on? I think after that we'll go deep into the last column, which is minimum violation planning. All right. So let's go over that. So minimum violation planning, as thank you for leading the question. So it operates on finite state system. In this case, we call it the weighted finite transition system. So think of this as a graph, right? So weighted finite transition system has the set of state S, right? The relation R, right? Which is a subset of S by S. So there is relation S1, S2 in R if we can go from state S1 to S2, right? So look, think of that as a graph. We have S init, which is the initial state. We have the set of atomic proposition and the labeling function. Think of atomic proposition as the properties that we care about in the system, right? So previously in the traffic light example, right, the atomic proposition would be green, red, and yellow, right? L is the labeling function that map a state to the label that of the atomic proposition that are satisfied in that state. And finally, we have a weight. So each transition will have the weight. And this could correspond to, for example, the control effort to bring the system from one state to the other state, right? And the weight so when we have a graph, right, we can start talking about a path, right? So a path start from the initial state, right, and then follow some of these transitions to another state, right? So given a path, we can use the notion of the weight in the transition, right, to define the weight of the path. So in this case, the weight of a path is the sum of the weight of the transition composing that path, right? So let me give an example before we get lost. In this case, we have, somehow I don't have, okay, let me do it this way. Can you see my mouse?
Yeah.
All right. So we have in this case, let's say this is autonomous vehicle, right? It's trying to do unprotected left turn. There is a traffic light here, right? On the other hand, there's an oncoming car. This is, let's say, human driven. So that's H here. A is autonomous vehicle. Now, let's say the finite transition system could look like this, right? So it is now at C8. So that would be initial state. We usually have this arrow with no origin that point to the initial state, right? So at cell C8, it could remain at C8. So it may apply a brake and remain at C8. Or it could move forward to C4, right? So C4 is this one, right? And at C4, it could remain in C4, or it could also go to C9, right? And at C9, it will stop because that's the goal. So this is one way of abstracting the continuous system into a finite set of state. I mean, this is a very simplistic or simple example, most simple that we can do with intersection scenario, right? Now the question that we could ask would be, so the autonomous car is already in the intersection, right? The light is about to turn red. There's an oncoming car. What should it do, right? So the traffic rules related to this is, first of all, it does not want to get involved in a collision. Right? On the other hand, it also does not want to stay in the intersection when the light is red. Right? The question that we need to ask is whether it's better to go cut in front of this guy or stop with the risk of being in the intersection when the light is red. Right. So that would be an example we would use in this lecture. Does that make sense?
Somebody wants to know, what does the weight function do? What does it mean? And they're asking, is it 0 and 1? Is it probabilities? Is it cost?
Yeah, this is, in this case, it's the cost. We can define it. So this is something that we can define, right? It's think of it as the control cost. In this case, the way I use this as an example is that when it remains in the same cell, that means the car has to apply a brake, then we incur the cost of 1. But this can be arbitrary in the sense that what we want as the control effort as the cost. Right? So in many cases, this would be like, some weight on the control effort that need to be put in, like, the steering and brake and throttle. Right? So if we want to do it more formally, that would be the case. But in this case, we just do very simple abstraction of the system.
And somebody wants to know about the other agents. I think they're confused about determinism and, how the other agents are modeled. Are they deterministic? Are they non-deterministic? How do you capture behavior?
In minimum violation planning, the other agents have to be deterministic. And also, the other agent would be represented by a finite transition system as well. Right? And then there will be a notion of how we compose our model with another model. I think I'm going to go over that in the maybe in the later slide.
Okay.
Yeah, so essentially we try to think of this as we discretize the time domain first, right? And at each time step within, this discretized time domain, we try to figure out what state the two cars could be at, right? And we generate that composed system consisting of the state of the autonomous vehicle and also the human-driven vehicle. So I think short answer to the question of whether the human-driven vehicle has to be deterministic, yes. So there are ways to handle the case where we are unsure of what the human-driven vehicle would do. So in that case, what we would do is to generate a duplicate of human-driven vehicle, right? So each duplication represents another possible behavior of that car. But that would mean that all of them has the same weight. Think of it as just another car.
Thanks.
Is that clear?
Yeah, I think people are more clear, but awaiting further details.
Okay.
Yeah.
All right. Okay, so this is the transition system. From the specification side, as I will show earlier, we talked about LTL earlier. Computers do not understand LTL. To make it computationally possible, we would translate LTL into what we call a non-deterministic finite automaton. And in minimum violation planning, we are particularly interested in what we call weighted version of it. So a non-deterministic finite automaton, again, is almost like a graph, right? It has the set of states, Q. Sigma is the set of alphabet. And there's this delta, which is a transition function that is a subset of state multiplied by the alphabet and the state, right? It will be clearer once we go to the example. We have the set Q0 of initial states, right? And F is the set of accepting states. And as in the weighted finite transition system, we have a weight associated with each transition as well, right? So let's look at the example on the right-hand side here, right? So this is an automaton, right? So we have two states, Q0 and Q1, right? Again, an arrow with no origin, that means Q0 is the initial state, right? So the set Q0 is just state Q0, right? In this case, sigma is A and B, so we'll see the letter A and letter B here, right? Q1 is the accepting state. So we usually indicate that by having this kind of double circle. Yeah, so that's the accepting state. Now, in terms of the transition function, right, we have Q0 with alphabet A, it goes to Q0, right? So that's the first one, right? Q0B go to Q1, right? Q1A go to Q1. So true mean it will accept anything, right? So any letter will satisfy true, right? Q1B also go to Q1 because it is true, right? Now the weight is indicated on the transition as well, right? The weight of going from Q0 with alphabet A go to Q0, the weight is 1, right? So it's this transition. Q0 B to Q1, the weight is 2, which is here, right? Q1 A Q1, so it's this transition has no weight, right? And same for Q1 B Q1. Now, given a run, right? So a run is a finite sequence of states over a word. So a word is the sequence of alphabet, right? Now we say that the weight of this run is given by the sum of the transition weight, right? So this is very similar to the weight of a path in finite transition system. And given a word W, the shortest run is a run that minimizes W, right? So given a word, so a word is a sequence of alphabet. There might be multiple possible runs, right, that correspond to this sequence of alphabet. We say that the shortest run is the one that minimizes the weight. Does that make sense?
Can you give us some intuition as to why we might care about the shortest run or the weight of that particular run?
Okay. So we will use, first of all, a run, especially accepting run, we will see that it corresponds to a run that satisfies LTL spec. So later we'll see that LTL spec can be translated into a finite automaton in the way that the automaton accepts the words and only words that satisfy LTL formula. So they are equivalent, right? And the shortest run, so we will define how we construct this automaton, right? And the shortest run in this automaton would correspond to the amount of violation of the rule. Let me explain that in more detail later, but that's the very rough explanation of why we are doing it this way.
Okay, thank you.
Okay, so we have example here, right? So empty word is just, Q0 because a run always have to start at the initial state, right? So in this case, there is 0 weight. A run that corresponds to a word A, so there's only one state, one alphabet A. So in this case, that means we start in Q0, right? Go to A, that means it go to Q0. So it has to be Q0, Q0. Right? The weight is 1 because it's only this transition, right? AA means it has to repeat this transition 2 times. So that's Q0, 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 and that's the weight of 2, right? And the last example is AAB. So A and B, right? So that's Q0, 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 and Q1. And the weight is 1, 2, and then plus 2, and that's 4, right? And when a run ends in an accepting state, we call that run accepting. So this is sort of a one-slide summary of automaton stuff. Does that make sense?
So this particular example is deterministic, right? But in
yes,
we
yes,
would get
yeah.
the turn. Okay.
Yep, this is a finite or deterministic finite automaton. You are correct, but it doesn't have to be. Sorry, I just don't pick a good example. So we talk about LTL, right? In this case, when we talk about minimum violation planning, when we want to minimize the level of unsafety, we use another interpretation of LTL. We call it a finite LTL. You can see that most of the symbols are the same as before. There are just some slight difference in the semantics, because now we look at a finite run instead of infinite run, right? So first of all, we say that sigma, so a run satisfies P, if and only if the length of the run is greater than 0, so it's not empty, right? And the first state satisfies P, right? So this part is the same as in LTL semantics, but the finite semantic add this condition on the length of the run, right? Next, phi means that the run also need to have the length greater than 1, right? And the next, which is the second state in the run, satisfy P, right? The other operators are very similar. It's just that in this finite semantics, because we look at the finite run, we add more conditions on the length of the run, right? And there's a theorem that says that a finite LTL can be translated into a finite automaton, right? As I said, in the way that the finite automaton accept the words and only words that satisfy the FLTL formula. So think of FLTL as something that is easier to read for human, but when we go to computation, right, we would use the finite automaton to represent it instead. Does that make sense? Okay, let's continue then. Okay, so in minimum violation planning, we also think of specification, not just a single formula, but it is a collection of many rules. Right? If you think about traffic rules, for example, there are many rules. You want to avoid collision. You want to satisfy the precedence at intersection. You want to stay in lane. So these are like atomic rules, right, that we want to satisfy. And in many cases, we cannot satisfy all of them. So the idea is to organize these rules into a hierarchy, right? So in this case, we have these 4 components of a specification, right? We have AP, which is the set of atomic propositions. This is just like atomic proposition we use in a finite transition system or in the finite automaton, right? We have phi as a set of finite LTL formulas over AP, right? So we have think of each of formula as atomic rule, right? Now we have this psi, which is a vector of length n, right? So think of this as a vector where the most important rules would be at the first coordinate of this vector, and the last one would be the least important rules, right? So think of, let's say, collision, right? We want to avoid collision. That's usually the most important rule. And, comfort or maybe less important rule would be at the later of the hierarchy. So that means we would sacrifice as much comfort as we need to be able to satisfy no collision requirements, right? And we also have is there a question?
Is it possible for 2 rules to have the same priority level in your formulation?
Yes. Yes, so two rules can have the same priority and can be at the same level. So the priority function map a rule into a number, right? So the priority function, think of it as the weight between rules in the same level. So I usually talk about this one as the level, right? And the way we defined the order of the satisfaction is based on lexicographical ordering. So that means once we find, so we go from left to right in the vector, right? Once we find a coordinate where one run is strictly less than the other, then we declare that that run is strictly better, right? So there's no need to go beyond the coordinate once we find one that is strictly less than. Right. And think of the priority function as the weight. So there could be rules that are at the same level, right? But there are weights between them. Right. Let me, if we have, okay, let me show you maybe some example. Maybe it would be clearer. I'm sorry, because I just took one lecture out of like 12, so there might be time where things don't make much sense. So let me see whether there's a good example. This one, for example, right? So let's say this is autonomous vehicle, right? There is a static object here, right? We have 4 possible path to go. A, clearly it collide with O, right? B, B will stay within lane, but it would violate the clearance. So usually one of the traffic rules would say that you have to give enough clearance, lateral clearance to object, right? So you shouldn't be laterally too close to any object. So B would violate that, but the vehicle would remain within lane. D, on the other hand, go to a different lane, but it will satisfy the clearance requirement, right? And C also go to the other lane, also satisfy the clearance requirement. So now the question is it more important to satisfy clearance, or is more important to satisfy stay in lane rule, right? So if you say that no matter what, you have to stay in lane, we would be happy to violate any clearance requirement. In that case, we could put clearance to be above stay in lane. Right? And on the other hand, we could say we want to put them at the same level, but we want to put some weights between them. So this kind of prioritized specification would allow us to do both of this. Does that answer your question?
Yep. Thank you.
Okay. All right. So this is how we specify specification of the system, right? And so, as I mentioned earlier, the main goal of minimum violation planning is to minimize the level of unsafety. What do we mean by that? So before I define that, let me define this operator called vanish. Right. So given a finite word W, right, A0 up to AN, vanish W just remove the coordinates that is specified I1 up to IK. Right. So it removes all those coordinates from this word. Right. And the level of unsafety is defined as, so first of all, let's look at the second term, right? The min over I such that vanish WI satisfy phi, right? So that means we want to minimize the number of alphabet we need to remove from the run, right? Such that the run will satisfy the spec, right? And we multiply this by the priority of the spec. So this is the level of unsafety with respect to only a single atomic rule. Right? Given a run, we can define how unsafe it is with respect to a single rule. Right? Does that make sense? All right. So Now, once we can define the level of unsafety of a run with respect to a single rule, now we can exploit the hierarchy we defined earlier to define the level of unsafety of a word with respect to the whole specification. Right? So in that case, it would be the vector of level of unsafety of each level, right? Where the level of unsafety of each level is the sum of the level of unsafety with respect to the rules within that level, right? Does that make sense? So what happened is that first we, given a run, right, we look at each formula phi, right, each atomic rule, and then we compute what is the level of unsafety with respect to that rule. Then at each level of the specification, right, we compute the sum of all the violations, right, and then we put them into the hierarchy. Does that make sense? Yeah, and in the end, we want to minimize this level of unsafety. Any questions?
I'm not seeing any questions.
Okay.
So maybe somebody in the class can try and repeat back what this means.
So if not, then I could go over the problem formulation, right? And then we can see whether we are still on the same page.
Yeah, I'm
so in a minimum violation planning problem, we are given a weighted finite transition system, right? So that's the very first definition. We are given the goal state. So a goal is described by a label in atomic proposition, right? So AP is the same set AP as in the weighted finite transition system. And we are given the prioritized safety specification, right? The problem is to find a finite path fragment of the finite transition system such that, so the most important thing is we want this path fragment to end in a goal state. Right, so it has to end in D. And among all the paths that end in B, we want to minimize the level of unsafety with respect to the specification. Right? And then, among all the paths that minimize the level of unsafety, we want to minimize the weight that is defined in the finite transition system. Right. So think of that as the control cost as the least important objective. The most important objective is to reach the goal. Right. The second most important objective is to minimize the level of unsafety. And finally, we want to minimize the control effort. Right. So this is the formulation of minimum violation planning.
Somebody wants to know what the trace is. Is it?
Oh, I'm sorry.
Is it the same as a run?
Yeah. So okay, a run. Let me go back a little to this one. So a run is a sequence of state, right? So it's a sequence of S, right? So S is a sequence of S is a set of state. What we mean by a trace is that we already abstract the state into the label, right? So at each state in the run, we apply the labeling function L, right? So a trace would be like a sequence of alphabet, right? So that is like a word in the finite automaton sense.
Got it.
Okay, so this is the problem formulation. Now, how do we solve this problem, right? So first of all, what we do is we start with, for each rule, right, we start with the finite LTL description of the rule, right? Now, there exists a way to translate this finite LTL FLTL formula into an automaton, right? There are some existing algorithm to do this conversion, right? But here, after we get the conversion, so let me give example. For example, when we say that always, right, not H4 and A4. Let me go back a little to this example, right? H4 means that the human-driven car is at cell C4, right? And A4 means autonomous vehicle is at C4. So not H4 and A4, always not H4 and A4 means no collision, right? And the second spec we are interested in is that always, not red, and the autonomous vehicle is at C8 or C4, right? So that means the autonomous vehicle is in intersection when the light is red. So we have two specifications in this case. Both of them are invariant formula, right? We can show that the corresponding automaton in this case only have one state, right? With the transition described like this, right? So as long as not H4 and A4 are satisfied, it has a transition, otherwise it would block. Similarly for A4, right? It's the same, so it has one state and it has a transition that satisfies this formula. Right? So there's a way to do this automatic translation. Once this translation is done, we would augment the automaton to this A bar, right, where we add all the transitions. So the transition in A bar would be Q times sigma times Q, right? So all the alphabet here will have transition corresponding to any alphabet in here. And for transition that already exists in the original automaton, it would have the weight of 0, right? And for the transition that does not exist in the original automaton, we put the weight that corresponds to the priority of this rule, right? So the step is we start with finite LTL, we convert it to a finite automaton, and then we augment this automaton to have all the transitions, right? And the extended transition would include the weight that would corresponding to the violation of that rule, the cause of violation of that rule, right? And we can show that any finite word, right, is accepted by this extended weighted automaton, and the weight of the shortest accepting run of this automaton for W will be equal to the level of unsafety with respect to this rule, right? And this answer the previous question of why we use the automaton, why we put the weight on the automaton, right?
So somebody has a question.
Yes.
Is it correct to consider the level of unsafety being equivalent or related to the amount of time for which the rule isn't satisfied?
Yes. Okay, so in the finite transition system, it corresponding to the number of, think of it as the number of states that violate the specification. I will describe later when, with continuous system, what does this correspond to? And it's exactly the amount of time where we violate the specification.
Thank you.
Any other questions? All right. Okay. So we talked about one rule, right? Now, when we, as I mentioned earlier, usually we have, when we deal with autonomous driving, there are multiple rules, right? And we put them into hierarchy. And in this case, we need to define how do we compose the rules together, right? So now we have the prioritized safety specification, right? Where we put the rules into the hierarchy, and at each level of hierarchy, we have multiple rules, right? So in this case, we have the new big weighted automaton, where the state is the cross product of the state of all the automaton corresponding to individual rules, right? The transition is all the transition, right? So Q times 2 to the AP times Q, right? So it has all the transitions. And Q0 is the product of initial state of the individual automaton, right? The final state is also the product of final state of the individual automaton. Now, the weight of each transition, in this case, is a vector, right? Because now we have the hierarchy of rule, right? So it's the vector of length n. So if we recall, big N is the number of hierarchy, the number of levels we have in the hierarchy, right? And at each of the level, right, it is the sum of the weight of the automaton of that level, right? So that's XI formula. Let me go through the example a little. So as in the previous slide, we have two rules, right? So P1 P1 is where we collide. So the first rule is always not P1. The second rule is always not P2. And P2 corresponding to the autonomous vehicle being in the intersection with the red light, right? So in this case, we put the rule in the hierarchy like this, right? We think that collision is strictly more important than the red light rule, right? So collision is the only rule at the first level, and the only rule at the second level is the intersection rule, right? In this case, we assign priority 1 to both rules. It doesn't matter because at each level there's only one rule. This priority function matters only when we have multiple rules in a single level, right? Now, the composed automaton, as we defined earlier, right, it will have the cross product of the state of both automatons. So in that case, it would be Q0, Q0, right? So now we have all the possible transitions, right? P1 and P2, not P1 and P2, right? So not P1 and not P2, P1 and not P2. Now the weight, right? So for the P1 and P2 transition, right? So in this case, it corresponds to this transition and this transition. Each has the weight of 1 in the original automaton. So the weight of the composed transition would be 1, 1, right? So the first number corresponds to the violation of the collision rule, the first rule. And the second number corresponds to the violation of the intersection rule, which is the second rule, right? So when P1 and P2 holds, that means we violate both rules. In this case, we have the weight of 1 and 1, right? For the transition not P1 and P2, so that means there's no collision, but we violate the intersection rule, right? In this case, the first number would be 0, the second number would be 1. The third weight is P1 and not P2. That means there's collision, but we satisfy the intersection rule. So we only have the weight 1 at the first coordinate, right? And the last one is where not P1 and not P2. So that means we satisfy both the collision rule and the intersection rule, right? So there's no weight in this case, right? So this is how we compose the rules together. And we can show that any word W over 2 to the AP is accepted by this composed automaton, and the weight of the shortest run of AP for W is the level of unsafety with respect to the prioritized safety specification.
So here in this case, the weights are, in a fixed assignment. Is there, like, from scenario to scenario, are there is there a need to ever have a different set of weights?
Yeah, so that we don't know. Our guess is yes, because think of it as when you have, you might even have different set of rules when you drive on a highway versus in a parking lot, right? So the set of rules, the set of specifications would be totally different, right? And in that case, I would imagine that, the whole hierarchy, the priority functions are all going to be different, right? So we have not tried that, but I think it will be different.
So is the thinking that now the vehicle is, has used some kind of a way to determine that it is now in a intersection scenario. It's a scenario by scenario basis that is triggering a certain set of rules.
Yeah, so I think eventually we might need to go there, that you have sort of like a high level finite state machine that trigger the set of rules that would apply. I think, so I don't know, honestly, we have not looked into that. We just look at what if we have a single specification that is prioritized, what can we do with it? Yeah.
There was also a question,
yes.
how do you get a level of unsafety for the whole run given all the set of rules? Is it the weighted sum of the level of unsafety for each rule?
So again, we have the level, right? So at each level, it will be the weighted sum. That's correct. But we also organize them into different levels as well, right? So for example, in this case, we put collision and intersection in a different level. So they are not weighted against each other at all. Once we find a run with smaller collision, that would clearly be more beneficial than another run with larger number of collision. In that case, intersection doesn't matter at all, right? This is a way to think of it as we put infinite weight on the collision rule, right? When you weight between the two. Yeah, so it allows us to say that this is the rule that so one possibility is that you only have one level, right, where all the rules are weighted against each other, right? But we don't think that is realistic, because, I mean, that would mean you need to find a weight between collision and comfort, right? And in most cases, you would trade all the comfort that you need to be able to avoid collision, right? So this kind of hierarchy, right, different levels would allow us to specify that.
And is this like some kind of approach that is applied in actual vehicles now, or it is just academic?
Okay, I think I cannot give a definitive answer, but if you,
like for are different AV companies, thinking of things in this manner in general, or are they trying to apply it?
So there are definitely some AV company that apply this technique. Yeah, if you look at the news, that's the company actually advertised the use of this technique. Where they try to argue that, oftentimes, I'll show you the video too. Not all the traffic rules can be satisfied, right? When you encounter an illegal parked car at the double yellow line, right? What can we do? We cannot wait there forever, right? We need to violate some rule. So what rule do we violate? Right? So this framework allows us to handle that kind of situation. Yeah.
Okay, I think there was another question. If I had a run not violating any of the rules, we take the minimum cost run.
Yes. So in that case,
indicated in the slides, considering that there are costs other than for violating a rule.
Right. So in that case, you would have a run that ends at B, right? And the level of unsafety is 0. So that means there's no violation. In that case, we would go to C to minimize the control effort, or the weight in the transition.
Okay. Thanks.
All right. So let's move on. So this is how we compose all the rules together. And the last step to solve this problem is to construct the product of So we haven't talked much about our original finite transition system, right? So that's the model of our system. And we have now the weighted finite automaton where we combine all the rules, right? Now we can define the product automaton, right, between the finite transition system and the finite automaton. In this case, let me go over that slowly. The set of state of this product automaton would be S union now. I will talk later why we need this now state multiplied by Q, right? So it's the product of the state of finite transition system and the state of the finite automaton with the now state. And the transition is defined. So for those who are familiar with model checking, this is the kind of construct that model checking also does, right? So for each transition from the finite transition system and the transition in the finite automaton, right? With the label coming from the labeling function applied at state t, right? So if Q with the label of t transition to p in the finite automaton, right? Then we would have this transition in the product automaton, with the weight being the weight in the product automaton, right? But also the weight of the transition. Right? And this is the way how, in the end, we could just do graph search to extract the shortest run, right? Now, to explain where the now come from, this is how we define the initial state of this product automaton. For each state in Q, right? So Q and P in the state of the finite automaton, with transition from Q to P, using the label from the initial state of the finite transition system, right? We would have the transition from now Q to S init P in this product automaton, right? And the weight of this transition would be the weight of the finite automaton, right? Using the label of S init. And the weight of the transition of the control effort would be 0, because it's just, transitioning. It's just a way to check whether initial state is a valid state or not. Right? The initial state in this product automaton would be the now state multiplied by Q0. So Q0 is the initial state of the finite automaton. Right? And the final state or accepting state is the product of state of finite transition system and the final state of the finite automaton. And with this construction, we can show that the shortest run in this product automaton from the initial state, right, to a state in the accepting state, right, that is a goal state, right? So B has to be in the level of S. So we find the shortest run in this product automaton. We project this onto the path fragment of finite transition system. This is the solution of the minimum violation planning problem. Right? So we start with, finite transition system. We start with prioritized safety specification. We can show that finding a path from the origin to a goal state that minimize the level of unsafety and the control effort can be reduced to a graph search problem, right, in the product automaton domain, right? So this is minimum violation planning. We could take, I don't know, a few minutes break where I can answer questions before I can go over some examples, and then if we have time and people are still interested, I could go to the continuous version of this. Is that okay?
Yeah, definitely. We have time.
Okay.
So everyone, questions? Or even just ask where you got confused or lost the argument.
Yep. Don't worry. I know this is quite dense, and it's my own bad that I don't do a good job at going through this.
Somebody wants
Uh,
examples before questions.
I got a
okay.
little lost on this slide actually. I was wondering if you could go through it again.
Oh, sorry, I didn't get that.
I said I got lost on this slide actually. I was wondering if you can go through it again.
Oh, yes. How about this? Let me give an example. Maybe it helped to clarify quite a number of things, and then we would go over more specific part where we don't understand. So
Sure.
let's revisit this intersection problem, right? Sorry, I cannot find my mouse in the presentation mode. So again, let's recap. We have this autonomous vehicle, TS, right, whose finite transition system is defined here, right? So it goes from, so it starts at C8, right? If it apply brake, it has the cost of 1 and it will stay at C8. It could apply acceleration, in which case it would go to C4, right, with cost 0. At C4, it could apply brake with cost of 1, right, to remain within C4. And then it could apply acceleration to go to C9, and that's the goal state, at which point only brake is applicable, right? This human-driven vehicle, TSH, right? So we have a very simple model that it will just keep going, right? So it go from C3, right? C3 is where it is, to C4, to C5, to C3, to C6, right? In which case it would stop. The traffic light, it start with green, right? So at this initial state, traffic light is green, but it is about to turn red. So the next state, it will become red and it remain red forever. This is our system. We can show that we can compute the parallel composition of this system. What that means is that each of the transition system take a transition simultaneously, right? So each of them can pick its own transition and then it move together. So in this case, it has a single initial state, right? So autonomous vehicle, the first state is autonomous vehicle is at C8. Human driven is at C3, and the light is S1, which is green, right? So this is the initial state. Now, there are two possible transitions out of this. If autonomous vehicle apply brake, right, it would transition to C8, all right? So it remain in the same C8 state. Whereas human-driven vehicle would go to C4 and the light go to red, right? Or another transition is that it apply acceleration, right? In which case it would move to C4, right? The rest of the system move to C4 and S2, right? So we could construct this kind of finite transition system that compose all these models together, assuming that they make the move at the same time. Right. So this would be the final system, right? The finite transition system that describe how the whole system evolves. Right.
So
Now,
what's the question here in this kind of example is that the other agents are also deterministic, and we may or may not know what their choice is. So we have to explore all possible movements of the other agent. So
yeah.
the other agent is totally deterministic, and the second is that if you have more than one other agent, then this graph can start to explode.
So again, one of the limitation of this approach is that it assumes deterministic execution of other agents, because in the end, we would pick the transition, right? And that means we have control over everything, but we don't have control over the other car. And that means we cannot pick what the other car is going to do. That means we cannot deal with non-determinism. What we could do in this case, where we are not sure how the other car is going to behave, is that we generate duplicate versions of the other car, right? Each duplication, each instance is one behavior. So in this case, we have the behavior of it just keep going. We could have another behavior where it just stay in C3, right? So that means we would have multiple number of cars instead. In that case, we can handle, but that means we cannot put in some probabilistic notion of, we think that it would move with certain probability, right? We cannot handle probability. But we can only handle deterministic environment.
So, I mean, an AV situation is never going to be, or I don't know when it would be deterministic unless you have control over the other agents. But
yes.
So this is, well, I don't know if this has limited use in the AV situation. So what other situations where?
So one key advantage of this that I would argue why we don't need to handle reactivity or non-determinism as much is this approach allows us to replan very quickly. So we would run this online, right? At each time instance, we create this whole model, right? And determine what we should do based on our best estimate of what the environment is going to do, right? And then in the next time step, we observe what the environment actually does, and then we compute the plan again. So this minimization planning rely on this fast replanning. It is as opposed to, so if you do, for example, probabilistic synthesis, right? Mostly because it takes so much time, you would do that offline, right? And just implement the strategy online. In that case, you need to have a good model of what the other car would do probabilistically. But you wouldn't regenerate the plan online, right? It's just too expensive. So the way we think about this is because in autonomous driving, it's just so hard to model what the other agent could do. So relying on, the current best observation is probably the best we could do. But if we are just...
Yeah, you would be working with the predicted state of the other agents, right? And the predicted state of the other agents could have also some distribution.
I agree. I totally agree. And that's a drawback. I could put it that way of this approach that it cannot handle yet. So in fact, we have not tried this with probabilistic synthesis. I mean, I have separate work that deal with probabilistic synthesis only, where we try to. So when we start to deal with probability, right, then we talk about minimizing or maximizing the probability of satisfying the spec. So if you combine that with minimum violation planning, we might have to talk about, minimizing the expected the expected level of unsafety instead. Right? And also what I found, I mean, you're absolutely right. Oftentimes when we apply machine learning and get, probabilistic estimate over possible future states, right? I still have a hard time trusting that probabilistic estimate. Oftentimes, okay, so I think what is correct is the number usually indicate that the larger number indicate that they are more certain. But I don't think it really corresponds to probability in the sense of a well-defined sigma algebra. Right? So usually the number we got is some number between 0 and 1, where the closer to 1, the more certain it is. Mm-hmm. It's more of a belief rather than probability.
Yeah, and there was one question from the class. So this graph scales exponentially with the time horizon and the number of properties, right?
Okay, so two things. It scale, yes. So you can see that the composed system, right, is the product of all this state. So it scales exponentially with the number of agents you have. So that is correct. Now, in terms of LTL formula, right, translating LTL formula into finite automaton, that's also exponential. Now, the good news is that if you look at many traffic rules, they are very simple formula. And in most cases, I mean, in this case, like, collision avoidance, even intersection specification, they are mostly very simple, just safety or even invariant formula. So usually the spec automaton is very small.
Okay, good. Thanks.
Any other question? Okay, let me give. Okay, so another. Wait. Okay, so we construct the compose system, right? Now the next step is to construct the complete automaton, right? That compose all the rules, and that's what we did in the previous slide, right? So we have this automaton AP, right? That correspond to both no collision and the intersection rule, right? So the third step is to construct the product of this automaton, right, and the transition system. And in that case, as I mentioned earlier, we have the initial state as the now state, and times the initial state of the finite automaton, which is Q, right? Now, it only have transition to the initial state of the finite transition system, which is C8, C3, S1. Right. In this case, the only state of AP is Q, so it transition to this. Right now, no property is violated, so the cost here is 0, 0, 0. Right. From here, if we apply braking, right, if autonomous vehicle apply the brake, it will transition to C8, right. The human-driven car would transition to C4. The light would turn red, which is S2, right. Whereas if autonomous vehicle apply acceleration, it would transition to C4. Right? The human-driven car would also go to C4. The light also go to S2. Right? So we could compute this product. Right? So this is the product of our system and also the specification, right? With the transition cost. Now, once this is constructed, so we just construct it based on the definition I showed previously. Once this is constructed, we can run graph search to find the path from the unique initial state here, right, to a goal state. So the goal state here is accepting state, right? So it has to end with Q, and it also has to correspond to autonomous vehicle being in C9. So it's these two states, right? So we want to find a path in this graph that minimize the cost to either of these two states, right? And we can show that it's actually this green path. So what we would do is the vehicle start at C8, right? It should apply the brake initially. It would violate the intersection requirement, but that's the best it can do, because otherwise, if it apply acceleration, it would go to C4 and then it would hit the oncoming vehicle, right? So it would apply the brake, wait until the human-driven car go to C5, then it would accelerate to C4 and then accelerate to C9. In that case, it would have 2 time steps, right, that violate the intersection property, right? So the cost here would be no collision, so the first coordinate would be 0. The second coordinate would be 1 plus 1 here, so that's 2. And then the last coordinate would be 1 because it applied brake at 1 time step, right? And this is the optimal path. We can verify that it minimizes the amount of violation based on our spec, right? So this is just a simple, cook-up example. But in reality, I think we have shown there are paper on rulebooks, for example, where we apply this to more complicated situations like the overtaking I showed you previously, and we need to figure out which path is the best path.
So these now these transition diagrams and the kind of each of the states that are possible, these are all so far generated manually, right? And they are kind of like you are almost like sitting on a table and thinking through the possible situations. Is there, have you looked at, or is it interesting to sort of look at different techniques for synthesizing these and for coming up with these transition diagrams from observations?
So actually, when this is applied, we would run all this in real time. So what we do in real time is, so I will tell in the next slide how we deal with continuous system. But so the only thing that is fixed and is offline is the specification. So the spec is fixed and is given a priority, right? Now in real time, what we do is we construct the finite transition system correspond to the AV at that moment, right? And also the environment. So we would construct the product or the compose system online, right? And then do the synthesis online as well. So this step, like, the step of, observing this oncoming car, coming up with its future states, and also observing the traffic light. So this have to be done online, right? We construct this product online as well. We also do this composition in real time and do this synthesis in real time. So all this we can do in a tenth of a second. So like, 0.1 second.
Wow, that's amazing. I think for anyone who's in the class here who is interested in doing a summer project or a fall independent study, looking at this in the racing context would be also very interesting.
Yeah. The thing about racing is that it doesn't have much of the rule, right? So this one is useful when you have to handle rules or specification, not just maximizing or minimizing the time of reaching the goal, right? You need to specify other properties in the way also.
Yeah, so there are a couple of questions here. So this graph, that you showed before, can be extended to infinite times since there are loops in each automation. How do you usually decide when to stop? And then there are
when to stop expanding the graph?
Yeah.
So usually we would stop it where the final. So I think what is interesting here is where do we stop this expansion? Usually we expand it up to either the final goal or your what is it called, the perception range. So in reality, what you can think about applying this is you plan for some short horizon, right? To a state that is closer to the goal than where you currently are.
Okay.
Any other questions?
Yeah, we can look at the continuous case.
Okay. So there was a question about going through the slides again. Is the example make it more clear, or I should go over some of the slides again?
I think the preference is to hit the continuous case a little bit.
Oh, okay, sounds good. All right. So now in continuous case, right, we are given, instead of a finite transition system, we are given a dynamical system as a differential equation, right? So this is where we have x dot equal f of x and u, right? In this case, x is a bounded domain, right, of the state, and u is the bounded domain of control input, right? We also have the initial state x in it. And we defined a finite time trajectory as a map from the time domain 0 to finite time big T, right, to the state, such that there exists control signal U, right, satisfying this property. Okay. So that's a trajectory. Now, given a trajectory, we define a finite time word with respect to a finite set of time instances as a sequence of sigma 0 up to sigma n, where sigma I is the label of x at ti. So ti is all these time instances that we want to evaluate this trajectory, right? And it's a timed word in the sense that it's not just a label, it has the time component in it. So sigma I is the label of trajectory at time ti, right? With the duration from ti to ti plus 1, right? And the final alphabet would be the label of x at tn, and with the duration up to the end of this trajectory. Right? So given a trajectory, given the set of finite time instances, we can define a finite time word. Now we define this set T as the finite number of time instances where this continuity of the label occur in the trajectory, right? And the finite time word of a trajectory x is this time word of x with respect to these time instances where the label changes, right? So we look at the trajectory, we figure out where the label changes, right? And we use those time instances to define the finite time word, right? And here we assume that the labeling function is defined such that all this exists and is finite. Okay. Does that make sense? So the first thing we need to define is, given a trajectory, a continuous time trajectory, right? How do we define the notion of a word as we have in LTL, for example? Now, one of the things we would do is that we would abstract this continuous system into a finite transition system. In that case, we use this structure called Kripke structure. Right? Kripke structure is very similar to a finite transition system. Right? So it has the set of states, a finite set of states. It has the initial state, the transition relation, atomic propositions, labeling functions. So all these are essentially the same as transition system, although it does not have the explicit actions, right? But here we have the delta function that describe that assign the time duration for each transition, right? So we have a finite number of states, we have transition, and we know how long it would take to transition from one state to another, right? Now we can define a finite path fragment of k, just like we have the path fragment of finite transition system. This is a sequence of states such that it starts at the initial state, right? And Si and Si plus 1 belong to the transition, right? So we follow the graph essentially. And a path fragment would produce a finite time word, right? So in this case, we have a sequence of L and D, where L is the label of S of each Si, and D is the duration of transition from Si to Si plus 1, right? And the last one would have the time duration of 0. Okay. Does that make sense? So this is the structure we are going to abstract our continuous system to. So I mentioned earlier there are many techniques of, how do we transform the continuous infinite state system into a finite transition system. There's a big literature on this, but in this case, let me focus on what we call concretization. Right? As opposed to, a typical abstraction, concretization means that we only sample a finite set of states from the original infinite state domains, right? So in this case, we want to, let me first define a durational Kripke structure is trace inclusive with respect to a dynamical system if S is a strict subset of X, right? So X is the original domain of the state, infinite state, and S is finite. The initial state of the Kripke structure has to correspond to the initial state of the original differential equation, right? And there exists a transition S1 to S2 in the crypt key structure only if there exists a trajectory X in the original dynamical system, right, such that it starts at S1 and ends at S2, right, with some finite time t, right? And the delta from S1 to S2 in crypt key structure has to be exactly the finite time t of this trajectory, right? And additionally, the label can change only once within this transition, within this trajectory. Right? So essentially what we mean is we want to construct a crypt key structure K that is an under approximation of our original system. If there exists a transition from one state to another in this crypt key structure, there must exist a way to bring the original system from the initial state to the final state as well, right? So what we can show is that for any finite path fragment of a trace inclusive crypt key structure, there exists a trajectory of the original dynamical system, right, such that if we remove all the consecutive elements of the word in the crypt key structure, we recover the word of the original trajectory. Right, so there are sort of we can say that this crypt key structure is essentially an under approximation of the original system. If there's a transition in the crypt key structure, we can find the corresponding transition in the original system. Does that make sense?
Yep.
Okay. Now, so we defined earlier what is the level of unsafety in the finite state domain, right? Now we have the real time domain. Right? In this case, instead of minimizing the number of states that violate the spec, we instead minimize the duration. So this di, if you recall, is the duration of the transition. Right? So we want to minimize the duration at which we violate the specification. Right? And again, we weight it by the priority as before. Right? The only difference is now we look into the duration, the real time duration, rather than just the number of states. Right? The rest follow as before. So given the level of unsafety, the level of unsafety of a path fragment of the crypt key structure with respect to a safety rule is, so now we want to minimize the delta. So delta, if we remember for the trace inclusive, that's essentially the duration of the transition, right? So we want to minimize the duration at which we violate the spec, right? And because K is trace inclusive, we can show that this corresponds to this definition here for the continuous equivalence. Okay. And so this is for a single rule. For once we compose the rule, we use exactly the same definition as in the finite state case. We order rules into hierarchy from 0 to big N, right? And for each level, we just weight them with the priority function. Okay, so now in the continuous domain, right, the problem would be now we are given a dynamical system, right? And so the only change is instead of given a finite transition system, we are now given a dynamical system, right? We are also given the goal states and also the prioritized safety specification. Now, instead of computing a sequence of states, right, we want to compute a trajectory such that this trajectories end in a goal state, right? And it also minimizes the level of unsafety among all the trajectories that reach the goal state. And among all these trajectories that minimize the level of unsafety, we want to minimize the duration, right? So this is integral from 0 to t. of 1t. So that means we want to minimize the time, right, among all the trajectories that satisfy the that minimize the level of unsafety. Right. So this would be the formulation in the continuous time domain. Before I go into how we solve this, is there any questions? All right. So to solve this, we will solve it probabilistically. We borrow the notion of or the idea from RRT star algorithm. So I guess most of you are already familiar with RRT, right? So RRT is where you try to randomly sample states and generate the graph. However, we know that RRT does not converge to an optimal solution, right? So there's some recent result in 2011 where Sertaj Karaman and Emilio Frassoli, they came up with an algorithm called RRT star, right? That is based on RRT. There's some small difference in that instead of connecting a state to the nearest neighbor, it connects to log n nearest neighbor. And there's the rewiring among these log n nearest neighbors also. And with this rewiring, it can ensure that asymptotically it would converge to an optimal solution. This is the video they show how RRT star works. So you can see how fast it is at randomly sample and generate this kind of Kripke structure, right? And converge to an optimal solution. So our idea will also come from RRT star algorithm. You can see at this point it's pretty much converges already, right? So it minimizes, in this case, RRT star only minimize the time or distance to the goal, avoiding obstacle. For us, we want to minimize instead the level of unsafety. So what we do in our case is, again, we try to incrementally build the product of the Kripke structure and the automaton, right? So the automaton that correspond to our spec can be built offline, but incrementally online, we would build this product of the Kripke structure and the automaton corresponding to the spec, right? So what we do is at each state, we would maintain J, which is the minimum cost to reach state Q. We usually call that cost to come. And we also keep the best parent of each state SQ. Right? So to construct this, we start with the initial state, right? And the Q0, which is the initial state of the finite automaton, right? And we also have the accepting state being the initial state multiplied by the accepting state of the automaton. J of Q is now 0. So Q, recall Q is the initial state, right? So it has 0 cost to reach itself. The parent of initial state is nothing, so it's a null state. Right. So what we first do is, so we start with just the initial state. We sample a state, right? Then for each S-prime that is near this sample state, we try to connect S-prime to S, right? So we try to create a connection that connect starting from S-prime to S. This is based on the steering function, right? So steer S-prime S means that there exists the controller that would bring a state from S-prime to S, right? While only change the label once, at most once, right? And if such a function, if such input exists, we would add SQ to Q prime, right, for all the Q. So that means that we would add the new sample state along with all the state of the automaton, right, the property automaton to our Kripke, to our product automaton. And we add SQ to the final state for all Q that is in the final or accepting state, right? and we would add the transition from S prime Q prime to SQ to the weighted product automaton with the weight defined in the weighted product automaton. And after that, we would update this state S. So this means we update the cost to reach S from the initial state, right? And this could be updated based on its parents, right? And at the end, we rewire S mean it look at all these near neighbors and rewire it if S becomes the better parents, right? And we keep doing this, go back to the sample, and with this process, it gives us an anytime algorithm to build the weighted product automaton online. Does that make sense? Right. It's essentially RRT star, except that we need to instead of adding a single state S, we add S along with the property automaton states as well, right? And the cost is defined based on the level of unsafety, right? So with this, the nice thing is the computational complexity is almost the same as in RRT star with the constant factor that is the size of this property automaton. And we can also show the same asymptotic optimality property, that the path that this algorithm extract would converge to the solution of minimum violation planning problem in the bounded variation norm sense as time approach infinity, right? So as we keep sample, our solution would converge to the optimal solution. Yeah, so this is sorry for the 2 full hours of this. It's pretty complicated, I have to admit, and please feel free to ask any questions.
So in this version, once you can do this RT based algorithm, you don't need to do graph search anymore. You already have the best path.
That's correct. So with RRT, each state essentially has a unique parent, right? So you can just trace back the state. So no graph search has to be done. You can also apply a similar principle to RRG as well. So RRG also converge to optimal solution, right? But it has many more transitions. Yeah, RRT star would be, would save more computation, right? You don't have to maintain as many transitions that wouldn't be used anyway.
And in practice, is 100 milliseconds fast enough to plan effectively with this?
So this is quite, if you really do random sampling, I think it might be hard to get something reasonable, right? So the key here is that, okay, so the property of this RRT star is if you plan for long enough, you would converge to optimal solution. In reality, if we want to apply this online, right, in real time, we don't have infinite time to wait until the solution converge. So you have to rely on a good sample. So what I mean by this sample state, right? It doesn't have to be random. You could guide. So most of the time you would drive along the center line, right? So that would be, one of the. So when you do the sampling, you should somehow concentrate your sample around the center line of the lane.
So
yeah, so coming up with a good way to sample this would be important.
Yeah, you could do some important sampling type setup. One thing that students in the class have found using RT or RT star is that sometimes the solution that it finds, put it like oscillates between two different path homotopies. It's not very stable. So in this one, it seems like it might be even worse if it switches between which constraints it violates. You could end up having sort of the worst of both worlds. Is there any way to sort of stop that behavior from happening?
Right. Yeah. So I think when you apply this, there are quite a little, all these corner cases that you have to consider, right? So you could implement something like what do we call hysteresis, for example, right? So that you favor the original solution more. Like, if the cost of the new solution doesn't reduce the level of unsafety too much, you would stick with the original solution. Right, so that's also one way to handle all this switching.
And so I followed most of the derivation, but let's say that the sort of the graph example that you showed had a bunch of static obstacles. So does this apply equally if there are other dynamic agents that just makes it harder, right?
Okay. So in this one, this is RT star, right? We don't apply minimum violation there. So when we deal with dynamic object, oftentimes we have to do something similar to this, right? Where you have to project in the future where the other objects would be. Yes, it gets tricky. And as I mentioned earlier, we cannot quite deal with non-determinism very well. So yeah, I think there's still a lot of work to be done in this domain. I think the key point here that I think I want you guys to I want to give us a message is that, in many of the synthesis algorithm, we rely on being correct, right? We rely on satisfying the spec. This framework here says that many times that is not the case, right? Actually, okay, if we have some time, let me show one video. Let's see. Give me a minute. Need to find where that would be. Maybe here. So it's a video from a real drive in Singapore. And what I want to show is how, so this is a complete run from Singapore. It's actually a very quiet time that we pick so that we can demonstrate, to authority or whoever interested, how often, even on the quiet road, how often we have to violate some rules, right? So this is all driving autonomously, applying minimum violation planning, right? So you can see already an illegal parked car, right? So let me go quickly here. So here we have to stop at the intersection for the red light. Yeah. In Singapore, we drive on the left-hand side. So we are not violating rules yet. So in this case, this is going to be quite tricky. Oh, well, not this one, but see, there's also illegal parked car here that we need to cross the solid line. There's another car that cut in front of us when we have the right of way. The upcoming junction, this will be quite a tricky situation. We have this truck that blocked the whole view, right? There's also oncoming cars, so we had to sort of inch out a little to observe it. So yes, we do have to deal with all this dynamic environment, right? So I mean, construction right in the middle of intersection, and we have the rule saying that we should not change lane in intersection, and construction worker walking towards us.
So some people asking where in Singapore is this? Is this near NUS?
Yeah, quite close. So this is the area called One North. It's the only area right now that Singapore allow autonomous vehicle testing. Yeah. Yeah, so that's almost the end of the run. But you can see that even in this pretty quiet environment, there are quite already a number of situations where we need to violate some rules, right? And if we rely on things like reactive synthesis, where we say that whatever the environment does, we need to satisfy the spec, we are not going to be able to go anywhere here, right?
Yeah.
So
I have,
the order of rules that you would have for a system like this, even for a quiet environment?
So sorry, can you repeat the question?
What is the order of rules? Like how many rules would you have in your set?
I don't remember the exact number, but in the order of, let's say, like 20 or so.
Okay.
Yeah, so if we look at the traffic rules, like as in the driving guide, there are interestingly not that many rules, and most of them there seems to be quite trivial. We don't even need like the full temporal logic power to express them. A lot of them are mostly just safety properties. Yeah.
have you or anybody explored coming up with the rule ordering based on data? That seems like something that could be learned.
I agree. I totally agree. That's really something we struggle a lot with. So it's not just rule ordering, but even just writing down rules is not trivial. So actually, initially, when we started looking into this, right, we even have some results translating all the DARPA Urban Challenge rule into LTL. And so we start with that. We wrote down all these rules, and as it turned out, first of all, traffic rule is incomplete. There are many things that traffic rule does not state, but it just rely on people being rational, right, being reasonable. People would not oscillate within lane, right? So there is no rule. You can go into any traffic rule at all. They will not mention anything about do not oscillate within lane, right? They'll just say, oh, stay within lane. But you will not find a human driver, a reasonable human driver that try to, drive like a little snake within the lane.
Mm-hmm.
Right? So this is something that traffic rule does not explicitly specify, but we need to understand that it's implicit. There are also terminology that is not very precise. As I mentioned, the rule ordering is not well understood right now. Also, just writing down individual rule is also not a very trivial problem.
Yep. Okay. I have one more sort of very abstract question, which is, obviously there's things like signal temporal logic, metric temporal logic.
Yep.
They also consider a notion of like level of violation or level of satisfaction. However, they're less about, how many time instances did you violate for? It's not like the integral. It's more like assign distance
Right.
metric to the set. So how do you square away the two things, and can they be combined or not?
Yeah, so we at some point right before I left the company, we did start looking into this. So with STL, you are right. So it has the notion of robustness, right? So it has some quantity that say how well you satisfy a rule, but sort of all the rules are at the same level with no weight between them,
Mm-hmm.
right? So it is as desirable to be almost hitting someone as almost not comfortable, right? So I agree that I think combining STL, the notion of robustness and also the importance of each rule is also an interesting research problem. I have not seen anything like that yet.
Yeah, I think with STL, one of the things that I've found is maybe you have a spec about acceleration and then another spec about, let's say, the steering angle. The relative magnitude of the units for each of the individual atoms is not normalized. And so it produces some very unusual results on occasion.
Yeah. We found something similar to, so we have not looked, and as far as I know, I have not seen any work that look into combining this notion, because now you have another dimension to look into, right? You have a robustness measure, and now how do you think about whether you prefer to be robustly not hitting someone versus robustly being comfortable, right? I mean, now there's sort of so many weights between these different rules and how well we satisfy the rules, right? It's going to get a bit tricky. I mean, probably not tricky in terms of how to solve it once someone gives you all the weight, right? But I think coming up with the weight is going to be quite tricky.
Cool. I think this was really awesome. I think a lot of people are in the chat are also saying thank you a lot.
Thank you.
It was very useful. I think it was really nice that you went deep into the discussion. It was also very complementary to what we were covering in this class. I mean, in the formal methods class, it's almost like this work is, it falls between the cracks of, what we are covering in this class and what formal methods classes teach things in a little bit too abstract kind of manner. So I think if there was time, even later to just go over the rule books kind of paper later on, whenever that would be very interesting.
I'll be happy to. And please feel free to. I know that there's a lot of stuff today. Feel free to reach out to me, ask me any questions about this.
Yeah, I also say that we do have a pressing problem related to this. We're about to do multiple car races, and we need to figure out how to score crashes. And this hierarchy idea is interesting.
I see.
From that perspective.
So I don't know if you know about this. At some point, Andrea Chensi, he organized a Ducky Town competition where he also come up with the rule books for the Ducky Town. So Ducky Town is almost like a scaled down version of urban driving, right? With the small car. But they have to satisfy rules like stopping at intersection and things like that. And he also have the rule books for this project. So that's probably something you can take a look at.
Okay, thank you.
Yeah, and you also had shared with me the Amazon's their deep drive paper, and I'll share that with the class too. I think that's very interesting for people to look at as different ways of racing, and they are focused much more on like RL based approaches.
Yep. Yeah. So all the slides I present today, the slide I presented today came from the course that Richard Marie and I just taught in Istanbul a few weeks ago, and that's why I'm stuck in Thailand right now. So all the lectures, computer lab, we had 3 computer labs, even minimum violation planning. If you want to get deeper into this, I'll send you the link, Rahul, and you can forward it to the students.
I sent it to them already.
Okay.
The calc link, right?
Yep.
Cool. All right. Let's thank Nok, and this was very, very interesting.
Thank you. Thank you.
Yeah. I just assume there's a virtual applause.
Yeah. Thank you.
Thank you.
All right.
Thank you. Have a good day, everyone. Bye-bye.
Sticking around for the whole time. I hope this was useful, and then we'll continue again with one-on-ones later this week. All right.
Sounds good.
Yeah.